morning, friends. I warmly welcome to all of you in the series of the subject of mechanics of solids. Up till now, in this series of the mechanics of solids, we have discussed the various chapters like the reactions on beams, shear force and bending moment diagrams of beams, and recently we are studying the bending stresses in beams. So now what we have studied up till now in the series of mechanics of solids, let us see in this particular PPT. We learnt in this series about the types of supports and beams, types of loads acting on the beam, determination of support reactions, plotting of SF and BM diagram of statically determinate beam, concept of bending stress and section modulus, as well as the concept of bending equation and moment of resistance. So now today's session objective is to draw the bending stress distribution diagram and calculate the maximum bending stress in a given beam. Calculate the bending stress with symmetrical as well as unsymmetrical sections, and today also we have to solve some of the numericals related to the strength of section. Let us revise the things that we have studied up till now. If we take any section of a beam and consider the free body diagram on either side, we find that there must be the three internal stress resultants at a section in general to maintain the equilibrium of a body. These three are bending moment, shear force and axial force. Now the effect that we are discussing right now in this series of bending moment. Let us take a one simply supported beam which subjected to the external loads. Now let us take a section. I will divide my beam into the two parts by taking a section XX over here, and if we draw the free body diagram of the left portion, so at a section XX the three resultant components named called the horizontal force, vertical force and the moments are developed. The horizontal force is termed as axial force, vertical force is termed as shear force, and this is nothing but the moment. Now this moment developed the compressive force on the top section part and the bottom fibers are subjected to the tensile force. These forces are developed. The stresses at a section is known as the bending stresses in a beam. Hence, the effect of the internal loads, the beam bands and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to applied loads. This couple is generated by the normal compressive and tensile forces in the section. So what the bending moment does the beam, that causes the compression on the one face and tension on the other face. Please refer the figure. Compression on the one face here on the top face and the tension on the bottom face, specifically right now in this particular simply supported beam. It causes beam to deflect also. Now in the previous series we have also studied this bending equation. The name of the bending equation is M over I is equal to F over Y is equal to E over R, where M is the bending moment, externally applied bending moment. It is also referred as the strength of section. I, that is the moment of inertia. F, that is the bending stress at a particular location at depth Y from the neutral axis. E, that is the Young's modulus, are radius of curvature of a section. Now what is section modulus? It is defined as the ratio of moment of inertia of a section about the axis to the outermost layer from the neutral axis, that is I by Y max. We have derived these equations also in the previous lecture, where I is the moment of inertia, Y max is the distance of the outermost layer from the neutral axis. Now M is equal to F max into Z, where M is the moment of resistance offered by the section, that is, it is maximum bending moment. Also, moment of resistance offered by the section is maximum when the section modulus is maximum. So what this means that M is directly proportional to the Z. Z is high, M is high. So moment of resistance offered by the section is maximum when the section modulus is maximum, and hence the section modulus represents the strength of section. Now there are certain formulas that we have derived in the previous session for the section modulus for rectangular section, hollow rectangular section, circular, as well as the hollow circular section. So for rectangular section, Z is equal to 1 by 6 BD square, where B and D are the cross sectional dimension of the rectangular section. Precisely B is the width of section, D is the depth of section. For hollow rectangular section, Z is equal to 1 by 6 capital D bracket capital BD cube minus small bd cube, where capital B and D are the outer dimensions of the hollow rectangular section. Capital B is the width, outer width of the section, capital D is the outer depth of the section, while small b and D are the inner dimensions of the section, hollow rectangular section. Precisely B is the width, inner width, and D is the inner depth of the section. If we think about the circular section, the Z is equal to pi by 32 d cube d diameter of the circular section. For hollow circular section, this Z is equal to pi by 32 d capital D, that is of d raised to 4 capital D raised to 4 minus small d raised to 4 capital D, that is the outer diameter of the section, and the small d is the inner diameter of the given hollow circular section. Now bending stress in unsymmetrical beams, we have discussed these things in the previous class. Because one or two problems we have to solve today, let us revise. In case of the symmetrical sections, please remember the words: the neutral axis passing through the geometrical center of the section. But while in case of unsymmetrical section, such as L section, T section, some of the I section, where the neutral axis does not pass through the geometrical center of the section, hence the value of y for the topmost layer or bottom layer of the section from the neutral axis will not be the same. So here, where the case of unsymmetrical section will be there, our intention is to find out the step number 1 is the location of the neutral axis, and the location of the neutral axis that we have to find out by using the concept of center of gravity. So first step is to find out what will be the location of center of gravity, that is centroid right now in this case, and from that we have to find out the neutral axis. From that neutral axis we have to find out the y top and the y bottom, and to find out the maximum bending stress we have to use the maximum value of y, either y top or y bottom. So now let us go to the one of the problem related to that for the T section. A cast iron T section, which is referred in the figure, the beam which is simply supported on a span of 8 meter. The beam which carries a uniformly distributed load of 1.5 kilonewton per meter throughout the length of the entire span. Question is, determine the maximum tensile and compressive stresses. A good question which has been asked over here, and just refer a particular figure which has been given to us. A T section, obviously it is symmetrical about the YY axis. See this arrow, this pointer going YY axis, definitely it is symmetrical, but this is unsymmetrical with respect to the X axis. So what will be the given data right now? The given data is length of the simply supported beam, which has been given as 8 meter. UDL, which is acting throughout the beam, is 1.5 kilonewton per meter, that is 1500 newton per meter. And to find out the position of neutral axis, the center of gravity of the section is to be calculated first. So now let us we found out this center of gravity right now by drawing the figure on this tabletop first. So see on this tabletop, this is a given section right now, T section. This flange width given 100 mm and the depth of flange is of 20 mm. The thickness of web 20 mm and this is the 80 mm, that is the depth of web. So as I told in the previously that it is symmetrical regarding the y axis, but we do not know what will be our x axis, and that is the neutral axis, we do not know. So our intention is to find out neutral axis. I will divide this whole T section into the two parts. If you refer this one, I will divide into the two parts. First part, second part. Now this 1 and 2, what will be the formula? Y is equal to A1 y1 plus A2 y2 divided by A1 plus A2. Now A1, that is the area of first part, A2 is the area of second part, we can find out easily. But y1 and y2 is the distance of CG of that area from the one of the face which we have taken as a reference one. So if I will select this bottom is my reference line, then this is my first part, then the CG is over here, from this to this it is y1, and the CG of second part is over here, that is y2. So if we are referring, what will be the y1? Y1 is nothing but 80 plus 20 by 2, that is of 90 mm. What will be the y2? Y2 is equal to 80 by 2 directly, the center of the rectangle, second one. A1 and A2 is precisely known. A1, that is 100 by 20, A2 80 by 20. So now please come on to this particular PPT. So A1 known as, Y1 known as, A2 and Y2 both are known as. If we are putting the value in this equation, y bar is equal to A1 2000 into 90 plus 1600 into 40 divided by total area of T section, that is 3600 mm square. Using the calculator, find out the answer as 67.77 mm. This is the distance of the CG or centroid from the bottommost fiber. So if you refer this figure, this is my neutral axis. This 67.77 is the distance from the neutral axis to the bottom fiber. So total depth available is 100. 100 minus 67.77, 32.23 is the distance from the top fiber. So we know this neutral axis exactly right now. That we found out 32.23 from the top face. Now next intention is to find out the moment of inertia of the section about the neutral axis. Hence let us go to this particular tabletop. So what is our intention? Our intention is to find out for this section moment of inertia. Section is known to us. The given section is this one. We know that I is equal to I1 plus I2. I1 is nothing but moment of inertia of my first portion or first rectangular one with respect to the neutral axis. I2 is nothing but the moment of inertia of the second part rectangle one to the neutral axis. So for this it is nothing but Ixx plus AH1 square. For I2 it is also Ixx plus AH2 square. What is Ixx? Ixx is nothing but the moment of inertia of my first portion about its own xx axis. The own xx axis for the first portion which is lying from the CG of its own. This is the xx for the first portion. It is nothing but 1 by 12 BD cube plus AH square. Area is known to you, 120. What is H1? H1 is nothing but the distance of the CG of the area A1 to the neutral axis. If we know this one, this is 67.77 and this is precisely 32.23. So what is H1? If we take H1 is equal to, it is this distance, that is 32.23 minus 20 by 2, or if you take from the bottom, H1 is equal to 80 plus 20 by 2, it is this distance, minus 67.77. Both answer must be the same. This is my H1. If we come to this particular PPT, please refer the PPT. So I1 is the moment of inertia of the top of flange about neutral axis. That is nothing but the moment of inertia of the top flange about an axis passing through its CG.